All right, so just to sort of recap where we left off and what we're doing today, today's going to be a little bit more interactive. We're going to all be working on Excel again. What I'd like you to do, if you haven't done so already, is go ahead and log into your computers, and if you could, pull that email that I sent where I attached an Excel file that was called Gauss points. We're going to use that today. Pretty extensively, so make sure that you have that file on you. I sent it to you, I think it was sometime last week, so you should have it. But real quick, to sort of go back and make sure we're all remembering what's going on, you all have had your take-home exams, so I know that it's like once you start covering new topics, I know how it's tempting to sort of just let all this stuff seep out of your head. So I'll really quickly sort of go over again what we did last time. So if you recall, this is really like the be-all, end-all for finite elements. This was it. We were able to derive pretty much a closed form, approximate solution for these load displacement problems that we've been doing. And remember, we had sort of two concepts that we tied together. We tied together the concept of energy balance, the idea that the energy going into a system equals the energy going out, with an approximate displaced shape. We assume what the displaced shape of an element looks like. We take that concept and combine it with energy balance, and lo and behold, we've got finite elements. And that's what we've got here. But it again raised that fundamental problem that this thing right here, this thing that I almost knocked over about 5 minutes ago, cannot do integration. That's not what it's designed to do. These things are designed to do two things: count and add. That's what they do. When you play, Mario or YouTube or WoW or whatever, I know it seems like, this complex, set of programming, and it is, but it's all hinged on counting and adding. That's really what it is. It's just doing it really fast. Now, what we did is we said, okay, we went back and we looked at, let's keep our discussion simple. Let's go back to our most basic fundamental element, a bar element, and let's explore, can we look at that integration a little differently? And I pulled a little magic trick, and I said, I'm just going to make up this new variable. So instead of expressing things as a function of x, I'm going to express them as a function of xi, this Greek variable that I made up. Now, I made it up for a very specific reason. If I look at my boundary, my region that I'm integrating over, if I'm looking at it in terms of x, I integrate from x equals 0 to x equals L. But if I look at it in terms of xi, I integrate instead, and I'll go through and skip all this. You all have seen this before. But if I look at it in terms of xi, I'm now integrating from -1 to +1. And that has significant advantages from a numerical integration standpoint. There are a host of numerical integration techniques, but in order for them to work, you need to define some reasonable boundary for your integration, and -1 to +1 is a very common one. Okay? So one thing to point out before we actually start talking about just the numerical integration is when you do this change of variables, you tend to be left with this term hanging around because of your variable substitution. When we defined a stiffness matrix, we said it was the triple integral over the volume of B transpose CB. It is still that, but when you convert it to this new coordinate system, you end up being left with this sort of algebraic remainder left over, and we call that a Jacobian in our world. That's really all it is. You can actually interpret some physical quantities from that Jacobian, but in the end, that's what it is, and that's what it's for. Okay, everybody good? So, again, we did this change of variable substitution because what we wanted to do is convert this calculus-based problem into something we can do with simple arithmetic. And I propose to you that there are a number of different numerical integration techniques we could use. I mean, you all have probably done things like the trapezoidal rule. You've probably even done something as simple as just remember that method of slices or rectangles where you just evaluate the function times the width and just sum them up. I'm sure you've done that before. Riemann sums. There's a number of them out there we could use. In finite elements, one of the fastest and most common methods that we use is a method called Gaussian Quadrature. And what we do is we turn an integral into a sum. I mean, that's what it was originally anyways. You're just summing up those individual elements and taking the limit as the width approaches 0. That's an integral. Now, the format is we evaluate the function at very special points and multiply them by associated weighting factors. Okay? So if we look at something simple like two-point integration, we say that this problem is subjected or has 4 unknowns. We have where, these 2 points, we want to determine where these points are. They're somewhere between -1 and +1, but they could really be anything. And we have these 2 weighting functions, these 2 weighting coefficients, if you will. Now, the way that we derive them, and I mean, you could have the same thing if you have 1-point integration, 2-point integration, 3-point integration, what have you. The way that we derive them is through polynomials. We assume that the function follows a polynomial trend, and then we say, all right, based on these pretty simple integrals, which everybody in this room should be able to do, I mean, you should be able to integrate x squared from -1 to +1. If you can do that, you can set this up as a 4 equations, 4 unknown type of problem. Now, for something this simple, this is actually a pretty complex set of equations to solve by themselves. Luckily, if you're dealing with 1-point integration, 2-point integration, and 3-point integration even, you can do them by hand. It's certainly not easy. When you get to 4-point, 5-point, 6-point, it gets a little ridiculous, like the solutions. Like if you actually look at the closed form, it's like 15 plus or minus the square root of 19,483 over the square root of 17. Like, it gets ridiculous. That's why when you look at Gauss point tables, they tend to be just decimal numbers. They use numerical techniques to solve for them. All right. If we do something as simple as a 2-point integration scheme, we assume for that analysis, or when we do our analysis, we find that our weighting functions are equal to 1, and our 2 magical points are plus and minus 1 over the square root of 3, which that comes out to be about 0.577. So according to a Gaussian quadrature scheme, we know that these 2 points are somewhere between -1 and +1, and I'm saying those magic points are about minus 0.577 and plus 0.577. And that's 2-point integration. If you're dealing with 3-point integration, you're going to have different weights and different sampling points. Same thing for 4 points, same thing for 5-point, and what have you. But in the end, I think you'll find that the methodology is pretty straightforward. Now, I want to explain this methodology by use of the following. Okay? This is an integral that I think is really simple to do by hand, the integral of e to the x. The integral of e to the x is e to the x. Evaluated from -1 to +1, you get e minus 1 over e, which, if you remember, e is the natural base. It's like 2.7812, whatever. All right. If you do the math and sort of round that out, you'll get an answer of about 2.35 whatever. Now, one thing I'll point out, this is certainly not a polynomial. This is a exponential using a very irrational number, right? Okay. We're going to evaluate this integral using Gaussian quadrature. We're going to take weights times the function. Okay? Everybody good? All right. So what I want you to do, if you haven't done so already, is open up Excel and specifically open up that Gauss point table. Now, I'm just going to do all my editing straight here on this Gauss point table, but you all have the data there in front of you. You can do whatever you want. All right. Now, what I'm going to do is show you all a couple things. First off, does anybody know how to do exponentials in Excel? Does anybody know how to do that? Like e raised to something? Ex, what is it? Go ahead. Well, you need the caret, but you need the e value, okay? If you look here, up here, all right, so what's the natural base? It's like 2.78 whatever. All right, if you hit equals exp and take the exponential of 1, that'll give you the natural base. EXP is the function in Excel that takes E and raises it to a certain value. Okay, that's what exponentials do. So if I hit enter, it's funny how that gives me 2.718, whatever, that's your natural base. All right, so what I'm going to do is this. I'm going to open up a new Excel file to sort of demonstrate the accuracy of what it is that we're doing. Oh, I need a new one. Plus, I want to make sure that the font's a little bigger so that you all can see what's going on. So before I do anything, I just want to have a little calculation here that actually lists what the exact answer is. And what is the exact answer of that integral? It's E minus 1 over E, right? So what I'm going to do is I'm going to say it equals EXP of 1 minus EXP of minus 1. Something about like that, right? Let me box that in and highlight it or something. I don't know. That is the exact answer to this problem. I just want to have that there for reference. Okay, everybody good? All right, now, if you want, you can do it like this. It was E minus 1 over E. Here, I'll give you all a second. You could do E minus, you could say 1 over E. Still get the same answer. It doesn't matter. All right. Everybody good? Now, in order to evaluate this method and make sure that you understand, we're going to start off at a pretty high integration scheme. We're going to start off doing 4-point integration. Okay? Everybody all right with that? So I'm going to set myself up a little table. First thing I'm going to do is I'm going to have a column of I values. And it's 4-point integration, so I'm going to say 1, 2, 3, 4. Everybody okay with that? If you turn the grid lines off so y'all can actually see what I'm doing. Everybody okay with that? Now, for each of these I values, I'm going to have two things. I'm going to have a weight, and I'm going to have a sampling point. So, since I like making sure everything's consistent and what have you, I'll put subscripts on this and put subscripts. Maybe I'll do that. Okay. Everybody see how I'm doing that? You don't have to put the subscripts on there if you don't want. I just did it for the heck of it. Now, we're doing 4-point integration, right? While you all are working on this, let's go here. 4-point integration, these are my sampling points and these are my weighting factors, right? So here are my weighting factors, here are my sampling points. I'm literally just going to copy and paste these directly into that table, okay? So let's see. Let me make that a little smaller, make that a little smaller. Okay. So we'll do the weighting factors. And the sampling points. And you can paste the values, you can copy and paste, you all can do whatever you want, it doesn't matter. Because again, this is numerical, it's going to be approximate, it's not going to be the exact answer anyways. Everybody okay with that? Now, the next step is we have to evaluate our function. What are we integrating? What is our function? No. For this example problem, what are we integrating? What's that? We're evaluating e to the x, right? Remember, let me go back to the PowerPoint. For this quick example, we're doing the integral of e to the x, okay? So my function in this problem is e to the x. Okay, so let me show you what I'm going to do. All right, so here's my table I got set up so far. I'll even zoom in a little bit. Okay, so I've got weighting factors and I've got sampling points. I'm going to calculate, if I've got x values, I'm going to calculate f of x values. Okay? Now, how do I calculate f of x? My function is e to the x, right? So I take the exponentials of those. Maybe I should do f sub xi and subscript that. All right, see how I'm doing that? I just took, here's my x values, I'd take f of x. If I was integrating the sine of x, I would take the sine. If I was integrating x squared times the tangent of 3 times pi over 2x, and that, I'd just do f of x, all right? All right, everybody good? Now, I've got the function. Now I'm going to take each of those values and I'm going to take the weights and multiply them accordingly. So, because I like to be consistent, do my subscripts. So remember, we're trying to convert this into a sum. So I've got these functional values. I need to know how much they're worth. So each of these values have a respective weight associated with them. What are those weights? These values right here. So what do? Equals that times that. See that? All right. What's the last thing that we do? Sum them up. Well, good golly gosh gee, look at that. Pretty nifty, isn't it? Does anybody have any questions? All right, you all do 2-point integration. And tell me what you get. I'm going to set up my answer while you all are doing that. turn the TV back on. Looks about right. Looks about right. Well, you won't need those 2 rows there, but yeah, there you go. Looks about right. So, about right. About right. About right. All right. So you all are probably seeing that that's your answer, about 2.3427, right? Now, while you all are working, you all don't have to do this if you don't want, but I'm going to go ahead and do a 3-point integration, do something in between. So paste formulas. And then I could have done that all in one copy paste. And do that. Sort of. That on there. Okay. So what you're seeing is now I went ahead and did we had 4-point and 2-point. I said, what the heck, let's split the difference and do a 3-point integration. Let me sort of summarize those answers over here on the side. So we'll say 4-point, 3-point, and then 2-point. We'll sort of box that in, center that up. So 4-point integration gave us that, 3-point gave us that, 2-point gave us that. And then here is our exact answer. So just sort of taking a moment and looking at some of these comparisons, I mean, this is a pretty powerful technique, isn't it? This isn't that complicated, but, you know, with something as simple as, let's say, 3-point integration, we're able to achieve an accuracy of at least 3 decimal places. 4-point integration, it's 5 decimal places. It's nifty how quickly this stuff works. And the nice thing is, when you start dealing in finite element land, where you're dealing literally with linear functions or parabolic functions and what have you, the convergence rate happens even quicker. Okay? A lot of times what you'll see on, let's say, planar elements like shell elements or something like that is you might see reduced integration where they only use 1 integration point, or 4-point integration, and that's it. That'll make a little more sense actually after what we do next. So I'll sort of leave it at that. I'm going to take this method, however, and I'm going to make it more complicated here in a second. Okay? So does anybody have any questions about what we're doing right now? You follow this. Okay? Because now I'm going to make it more complicated. Everybody good? All right. Now, okay, so let me go back to this and talk about this methodology. If you go back before and look at our proposed, generic integration scheme for finite elements, we're not dealing with a single integral. We're dealing with at most 3. So what we need to now do is discuss how do we do multiple integrals with Gaussian quadrature. Okay? To do a single integral, we just do a single sum, right? What about multiple integrals? What if we've got that? What if, let's keep it simple. Let's say a double integral. Okay? Well, remember, how do you do double integrals? You all remember Calc 3, right? How do you do double integrals? You do the inner integral, get an answer, then do the outer integral. And just keep working in that fashion until you arrive at your final result, right? Well, do the same thing here. So this inner integral is a sum, right? We convert that into a Gauss quadrature sum. Then we take the outer integral and do the exact same thing. So when you evaluate this, can you do Gaussian quadrature for multiple integrals? The answer is absolutely. Okay. The scheme is a little more complicated, but not really. It's actually not that bad. Okay. Now, one of the things that you really want to make sure that you understand is how many terms you're going to be dealing with for a given integral. Okay? If you remember what summation notation means, like if I go from I equals 1 to 3, I go I equals 1, I equals 2, I equals 3, right? But if you've got a double sum, you have to go through both sets of indices. So look at this. Okay, I have here sort of a demonstrative example to give you kind of an idea of what's going on. Let's say we had a double integral and we were doing 3-point integration. So we go from I equals 1 to 3, but we're also going from j equals 1 to 3. So watch what happens. Okay, this right here, I equals 1, j equals 1. I equals 2, j equals 1. I equals 3, j equals 1. Now it's I equals 1, j equals 2. J equals 2, j equals 2. Then j equals 3. J equals 3. So let me ask you this. If we were doing 3-point integration, we would have a total of 9 terms. Does that make sense? Because we'd go through the I equals 1, I equals 2, I equals 3, and each of those we'd have an iteration, right? So this is in general, if you're doing Gaussian quadrature, how many terms you're going to deal with is the number of Gauss points you're considering raised to the number of integrals. So quick question. If we had a triple integral and we were doing 3-point integration, how many terms would that be? Pop quiz. Triple integral, 3 points. So what is that? Nope. It's 27. It's 27 terms. Okay? Do you see that? Does that make sense? Okay. All right. So the same process still applies if you go to triple integrals and what have you. So let's do a complicated one. All right. All right. Now we're good. Now instead of dealing with or just e to the x, we've got e to the x and we've got a cosine. Now you all have had calc 2, so you remember these whole hyperbolic terms. Y'all remember that? That this hyperbolic sign is not really a trig function. It's really more of an exponential function. But it behaves a lot like a trig function. That's why we call it that. Okay? Now this is the integral of e to the x times the cosine of y. Okay? Now, if you do -1 to +1, -1 to +1, actually do it by hand, this is your analytical result. It's about 3.96 or what have you. We're going to do the same thing using Gauss quadrature. Everybody all right with this? Okay, now, let me go back to my Excel sheet. Okay. All right. View grid lines. Okay. Now, the first thing I'm going to do is, like before, I'm going to have the exact answer. And what was it? It was 4 times the sine of 1 times the hyperbolic sine of 1. So that's equals 4 times the sine or hyperbolic sine of 1 times the sine of 1. That's what we got, right? That's the exact answer. Everybody good? Okay. Now, let's do a long one. Let's do 4-point integration. So pop quiz. If I have 4-point integration for this problem, how many terms am I going to have? 16. Now, how do we come to that conclusion? Let's go back to what we did before. Before, we listed this single index I, right? And this single index, if we had 4-point integration, we had I equals 1, I equals 2, I equals 3, I equals 4, right? Now what I'm going to do is I'm going to have 2 boxes. and I'm going to have a term of i's and a term of, or a column of i's and a column of j's, right? So you said 16 terms. Let's see if you're right. All right. So let's start off with the i's. Let's keep it simple. So i's are going to go 1, 2, 3, 4, then 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4. I mean, how does the sum work? You just keep cycling through the indices, right? What are the j's going to look like? Let's see, you tell me. Remember, I've got to go through each permutation. So this is, there we go. It's going to be 1, 1, 1, 1, whoop, 1, 2, 2, whoop, 2, 2, 2, 3, 3, 3, 3, 4, whoop, 4, 4, 4. You see that pattern? Now, if you look at this, no two rows are identical. No two rows are identical. Like this is row 3, 2, and this is row 2, 3. None of them are identical. I've gone through every possible permutation of I and j combined together. Make sense? Now, next thing I'm going to do is I'm going to put my weights. Okay? So I'm going to have a weight of I values and a weight of j, or weight for the I indices and a weight for the j indices. Okay. Everybody okay with this? All right, watch this. Okay, so we're doing 4-point integration, right? So I'm after these yellow numbers right here. Okay, so these are my weights, right? But keep in mind, these are the weights as the indices cycle through. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, right? So I propose to you that the I indice weights look like this. And if you look, what you'll see is that every 4 terms, the pattern repeats. Why does every 4th term, why does the pattern repeat? Because look at your indices. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Does everybody see that? Now, what should all these weights be? These ones right here. The 3.347. Does everybody see that? Because j is 1, right? Do you see the pattern? All right. So this term goes here. All of those places. This term goes here. Oh, goodness. This term goes here. And this term goes there. Might be somewhat new to you, but does that pattern make sense? That for the I terms, I'm literally repeating every 4th one. But the j terms, these indices are all the same. So these terms better all be the same. These indices are the same. These indices. I did the weighting functions. Can you all do the sampling points as well? It follows the same pattern. There's going to be x terms But over here, there's going to be y terms. But again, it follows the same pattern. All right? Let me do some formatting. All right, so, oh, where'd my Gaussian? Okay, so now I'm looking at these. I'm looking at these red numbers. Okay, so again, for the I column, it's going to be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. For the J column, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. See how I'm doing that? I can say, all right, paste formulas. Do that. And then this formula, repeat that one, repeat that one, repeat that one, and repeat that one. Maybe I'll shade these up a little bit so it's a little easier to see them. Make these like that. I'll sort of give you all a moment to help set this table up, or give you some time to do that. See how you all are doing. Looks good. Exact answer is right here. 4 times the hyperbolic sine of 1 and then times the sine of 1. Remember, we're doing a double integral and the problem's different. So, as we've got this integral. Integral. That's the integral we're evaluating right now. Looks good. Looks good. Okay, now, what I'm now going to do is I'm going to set up a similar column. Because I'm lazy, I'm just going to use the format painter. Set up green color. And now in this green column, I'm actually just going to evaluate the function. Now, what is our function? It's this right here, e to the x times the cosine of y. So what I'm going to do is I'm going to say equals the exponential of x times the cosine of y. Everybody see that? And drag it down. Oh. Not too bad, right? Last thing that we need to do is actually do the weighting functions on here. So again, I'm lazy, so delete all this out. We need to take this function and multiply it times the weights. So because we're doing a double integral, we've got two weights. All right, so I'll give this another color. We'll make this yellow. So what I'm going to do is, it's the same pattern as before. The problem's a little bigger, but it's no different. I've evaluated the function. I take that function and multiply it by the weights. So equals that times that times that. Drag it down. And what do I do at the very end? Sum it up. And 3, 2, 1. Marker drop. Pretty nifty, isn't it? Oh, you've got too many hyperbolics. It was 4 times the hyperbolic sign times just the sign. The what? Oh, it's this. So I'm taking the exponential of the x times the cosine of the y's, because that's what I'm integrating. I mean, if I was integrating, tangent of x, y squared, I'd take the tangent of x times y squared and then just do that. It works regardless of what function you're looking at. Make sure you all have gotten that terms out. Excuse me. I know some of you probably feel like you went back to a math class today, but there is an applicable reason for why we're doing what we're doing. I want you to understand this methodology, because when we see, everything that we've been doing right now in finite elements has arguably been very basic. We've just been talking about line elements, like a bar, a beam. Man, things in the real world are much more complicated. If you go back to some of those examples we looked at in the very beginning of the semester, we're talking about three-dimensional finite element analysis, brick elements, shell elements, plate elements, isoparametric elements, plane stress, plane strain. That is far more complicated than anything we could do by just taking a bar and yanking on it. We can do element formulation actually pretty easy. The hard part is the integration, but that's where this comes into play. Okay? We can numerically integrate and get an answer close enough for government work. Okay? And when you actually go through and run, real life finite element programs like Abacus, ANSYS, and I say real life, I'm talking about the heavy duty ones, the ones that can really do the powerful complex analysis. Uridinas, Abacus, ANSYS, LS-DYNA, Lucis, stuff like that. Those programs are built based on these principles. Simple stuff, just exploited as much as humanly possible. All right, does anybody have any questions? All right, this is actually all I have for you all today. What I do want to preview, though, for what comes next is what's called an isoparametric formulation. And I know that sounds like a nasty word, and I know it sounds like, oh my goodness, I about had it with all this theory. I mean, gosh, the Gaussian quadrature was enough. But it has a particular point. What I want to do is I want to be able to formulate elements in 2 dimensions and in 3 dimensions. See, if I go back to the way back beginning, just sort of a, life flashing before your eyes, but it's finite elements. All right. If you go back to like some of the stuff we were looking at on day 1, we were looking at finite element analysis of complex 3D structures. This is stuff you can do with finite elements. This is stuff you can do with finite elements. 2-dimensional, 3-dimensional, you can do this complex stuff. We haven't talked about any of this yet because we've been restricting all of our discussion to bars and beams. Why have we been restricting our discussion to bars and beams? Because bars and beams is the only stuff we can really do by hand. After this numerical integration stuff, it's actually going to get real in here. We're going to do real finite element analysis. So in the not too distant future, a lot of this theory in this class is going to end, and we're going to open up some real programs and do some real analysis. It's going to be a lot of fun. Everybody good? That's all I got for you all today. I will see you all next time.